To the untrained eye, standard enterprise network hardware is visually indistinguishable. These two units, a 1U network switch and a 1U edge router, share a chassis size, metal housing, and identical rows of Ethernet ports. Yet, according to the Open Systems Interconnection, or OSI model, these two devices handle data at different architectural layers. Switches act as the high-speed transit engines of the local area network, pushing data between computers in the same office. Routers serve as the gatekeepers that determine how that data navigates the global web of disparate networks. The real divergence reveals itself under the chassis. One board is dominated by a massive application-specific integrated circuit, or ASIC heatsink. The other relies on a traditional CPU and RAM motherboard layout. To understand exactly where and why network architects deploy each of these devices, we must dissect their operational logic, analyze how they manage traffic boundaries, and test their physical hardware limits. Misunderstanding these core hardware constraints determines whether an enterprise network scales gracefully or collapses under its own traffic. This diagram isolates the data structure used at OSI Layer 2, the data link layer. It deals exclusively with Ethernet frames. Notice the header. It relies on flat, 48-bit Media Access Control, or MAC, addresses to physically identify the sender and the receiver. When this frame enters port 1 of our switch, the hardware passively listens. It reads the source MAC address and writes a new entry into its Content Addressable Memory, or CAM, table, mapping that specific hardware address to port 1. Next, the switch looks at the destination MAC address. If that destination is already recorded in the CAM table, the switch routes the frame out exactly one specific target port. If the destination MAC is missing from the table, the switch has to ensure the data arrives. It duplicates the frame and floods it out all remaining active ports simultaneously. This operational logic is hardwired directly into the switch's silicon through application-specific integrated circuits. By etching the rules into hardware, the switch bypasses the slower processing cycles of a software CPU. It performs these MAC lookbacks and forwarding decisions at wire speed, resulting in negligible processing latency. While ASIC-driven switching delivers high-throughput local speed, its fallback mechanism of flooding unknown frames creates a structural vulnerability as the network expands. In a purely switched Layer 2 network, all interconnected devices share a single broadcast domain. This means a broadcast frame, a message addressed to every device on the network, is received by every single node. Look at this topology of 50 daisy chain switches. When a single device sends a broadcast, the first switch floods it to the next, which floods it to the next, propagating the signal across every single link in the array. If a loop forms, these broadcasts multiply. The resulting broadcast storm consumes all available bandwidth and crashes the interconnected hardware. The switches cannot stop this chain reaction. Flat MAC addresses act like hardware serial numbers. They contain no hierarchical location data, giving the switch no way to isolate or filter the traffic. Layer 2 switching optimizes local data transit, but without a higher-level mechanism to enforce traffic boundaries, that local efficiency eventually triggers a network-wide failure. To sever these broadcast domains, we must move up to OSI Layer 3, the network layer, and introduce the router.
The router provides an immediate physical defense. When a Layer 2 broadcast frame hits a router interface, the router explicitly drops the broadcast, containing the noise to a single local segment. To transit data globally, the router discards the local MAC addresses. By stripping the Ethernet header, it exposes the underlying Layer 3 IP packet. IP addresses are structured logically, providing the distinct network ID and host ID needed for hierarchical routing.
The router determines the path using longest prefix matching. If the routing table contains overlapping paths, like a /24 and a /27 network, the router selects the entry with the longest, most specific matching prefix. Once the path is set, the router must prepare the packet for its next physical jump. It encapsulates the IP packet in a brand new Layer 2 frame, stamping its own MAC address as the source and the next hop device's MAC as the destination. High-performance routing manages this complex math by separating the architecture into two distinct systems, the control plane and the data plane. The control plane is the system's brain. It uses the CPU and protocols like OSPF to map the network topology and build the routing table. The data plane is the hardware muscle. It takes rules from the control plane and pushes user traffic across interfaces without interrupting the CPU. Routers trade the raw velocity of MAC switching for intelligent, hierarchical control. They segment the network, translating local hardware signals into the logical directions needed to connect the globe. Dedicating a distinct physical router port and separate switch to every corporate department is financially and physically prohibitive. This diagram shows how virtual local area networks, or VLANs, solve this by logically partitioning a single physical switch. We can map ports 1 through 10 to VLAN 10 for the blue department, and ports 11 through 20 to VLAN 20 for the yellow department. These virtual boundaries act like physical walls. A broadcast originating from a blue port reaches only the other blue ports. It stops at the boundary, leaving the yellow ports dark and immune to the traffic. For a machine on the blue network to communicate with one on the yellow network, the traffic must leave the switch entirely, hit a Layer 3 gateway, a router, and be routed back. We connect these virtual networks to a router over one physical cable via the 802.1q trunking standard. To keep the traffic separated over one wire, the switch modifies the Ethernet header. It momentarily splits the frame to accept a 4-byte tag containing the specific VLAN ID number before pushing it up the trunk link to the router. VLANs give architects the power to dictate broadcast boundaries through software configuration, shrinking collision domains and allowing the campus edge to scale. This intersection of hardware and software generated a hybrid device, the Layer 3 switch. It executes routing functions using the acceleration of switch ASICs. This raises an engineering dilemma. If a Layer 3 switch can route inter-VLAN traffic internally at wire speed, why would an enterprise invest in a traditional router with lower port density? The answer lies in the weakness of ASIC architecture. Silicon chips are fast, but they are rigid. They lack the memory overhead required to track complex, dynamic, stateful network connections. Look at this split screen of NAT overload. The ASIC on the left queries a static table, while the right CPU actively maps thousands of internal IPs to the internet. Terminating encrypted IPsec VPN tunnels demands dedicated router crypto processors, overwhelming standard switch ASICs. Furthermore, true routers offer physical media diversity. They natively accept specialized inputs like fiber, LTE, or DSL interfaces, hardware standards that campus switches do not support. This establishes a clear, strict architectural rule. At the access layer, deploy pure Layer 2 switches to provide high-density connectivity for end users. At the campus core, deploy Layer 3 switches. They possess the internal backplane capacity to route massive volumes of traffic between internal VLANs using ASIC acceleration. At the WAN edge, deploy true routers. They interface with the internet, managing heavy NAT states, firewalling, and exterior protocols. Mastering enterprise infrastructure means deploying the specific combination of silicon and software required to balance local velocity with global security.